Okay, just to clarify where I ended up this morning, because people asked me about it, so let me say it again. We did two calculations. One was in perturbative Yang-Mills, but a semi-classical calculation of a propagation amplitude in Euclidean space, and it came out looking like this. So this is just the on-shell action, the on-shell world line action of a relativistic particle. And with mass m, there was a Wilson loop expectation value here, which perturbatively seemed to have no corrections. In other words, was the same as a trivial thing, the trace of 1, which is n. This is the weak coupling side, lambda much less than 1. Then we went over to the string side, which is supposed to compute lambda much greater than 1. And we found an expression that looks something like that from studying the string sigma model with basically the same trajectory of W boson. Also, it was more or less a disk amplitude that we had, so you could think of this as something like 1 over G string in front of this. But given that we don't evaluate the rest of the prefactors of this exponential, this is less important than the form of the exponential itself. And then the observation is that these are both very similar. In fact, they're almost identical. And what you would draw from that is that it's at least consistent with, if not directly implying that, the Wilson loop, which goes here, is trivial. And one can identify the mass of the W boson by this formula, that this mass factor here is just equal to this thing. And that, in fact, is what the naive guess at the mass would tell you. It's just the distance between the probe brane and the stack of D3 branes times the effective string tension here. So this would be no surprise. It has the square root of lambda in it, but that's okay. You can just absorb it into the R0. You can use this formula to define what you mean by R0. And then plugging it in here, all vestiges of string theory parameters would be gone. Right? Everything is a gauge theory parameter, although there aren't very many of them in this formula. Okay, so now I would like to do this over again for a slightly more sophisticated scenario. And that's a scenario where we should calculate the Wilson loop of a circle. So what I need is a slightly more elaborate dynamical setup where I force the W boson to go in a circle. So the W boson is a bifundamental field. It transforms under the fundamental representations of the gauge groups of the stack of n D3 branes. So a fundamental representation of the SUN and of the gauge group of the other probe brane, which is U1, which means it's U1 charged. If it's U1 charged, we can manipulate it with a U1 electric field or a magnetic field, some gauge field. That field is imposed in the world volume of the probe brane. Right? In a sense, the SUN n equals 4 super Yang-Mills theory fields live in the world volume of the D3 branes. I point to them being here, and I guess if they have to be somewhere, this is the best place to put them. And the U1 field lives here. So we can think of putting a background U1 field that would force this guy, instead of to go in a straight line, to go around in a circle. And then we can study the analogous problem there. So on the field theory side, what I would do is I would write down the same world line action, but couple an electromagnetic field. So that would look something like this. Okay, so this is exactly the same one that we had before. And then if we had a constant electromagnetic field, it would look like this. The A mu for a constant F mu nu is F mu nu over 2 times X nu. And then this is the usual A mu times X nu dot coupling here. And let's say F01, well, not 0, 1. This is Euclidean space, so 1, 2, the first 2 dimensions. But we'll call it an electric field. That's because in Minkowski space it would be an electric field. Of course, in Euclidean space, an electric field looks the same as a magnetic field. And its purpose here is to force this particle to go in a circle, which is basically just the Landau orbit of the charged particle in a magnetic field. Okay, so the equations of motion for X look something like this. Actually, I don't think an I belongs here. In fact, I think this was a plus sign in my notes, because otherwise this would be inconsistent. The equation of motion for X now looks like this. Before it didn't have this term, so now it has it. So this is the Lorentz force on a relativistic particle. Right? This is basically the acceleration term. And then for the t variable, the proper time, it's just the same equation. It looks something like this. Okay, so these can easily be solved. The trajectory is like a circle. So the classical solution of this stuff looks like this. The circle is given by the strength of the field, actually the mass of the particle divided by the strength of the field. So the heavier the particle, the bigger the circle. The smaller the field, the bigger the circle. The bigger the field, the smaller the circle. So it's just like a cyclotron orbit. And then it goes in a circle in the plane, say in the 1, 2 plane, in the same plane that the field is in, like so. And then, if you go and plug this thing into the action, and the solution for t, let's see, t squared is, well, t has some solution. You can get it by plugging this into here and figure out what t is. So then you have to plug this and this into the action. The action has 2 terms. One is 2 pi times the radius of the circle. And then the other one comes from the electromagnetic interaction, which also has basically the same form, except it's something like the magnetic flux times the area of the circle, which is what this would be. This is like the integral of A, so you use Stokes' theorem to write it as the curl of A inside, and that's basically the constant flux times the area, pi r squared times E. So it looks like that with a minus sign. And of course you can combine these. I wrote them like this because we'll discuss this later. You can combine these to be minus there's something wrong with this one. The area of the circle times the mass, so this should be squared. and this should be r squared. What is r? R squared is m over e squared. And then you recognize the same functional form here. This is minus pi m squared over e, which is something like the exponent in the amplitude for what's called the Schwinger effect. And indeed, this is, in a sense, an instanton calculation that one might do to find that effect. We don't really care about the effect here that much. We just see that the field has forced our particle to go around in a circle. So now if we took and used this result, why the minus sign here? Here. Oh, it's plus. Yeah, good. Sorry. It's a misprint. Because t is a constant here. Yeah, it's like the Schwinger proper time. So if you go to if you introduce an Einbein to make a reparameterization invariant action, in a sense t would depend on the time. But you can gauge fix to make it a constant. So that's what I've done here. So it's a constant, but it still has to be integrated over, which means one should still solve its equation of motion. Okay, but since it's a constant, when you vary it, you basically have this integral going with x dot squared. It just sort of follows it. Right? All right, so this equation basically comes from taking a derivative of this action by t and setting it equal to 0. Right, it's not a functional derivative now, it's just a derivative. If t depended on time, it would be a functional derivative, and then you're right, the integral wouldn't be there. It would basically be the same equation. But here it's just been gauge fixed already to be a constant. So I use this form of the proper time action simply because it's this form that one can easily derive just by the Schwinger parameterization of the two-point function. It comes out just like this. Okay, so where do I use this? Well, of course, in this world line path integral. This should give something like the semi-classical approximation to it. And so the world line path integral computes an amplitude that looks like this. And then if we couple it to the n equals 4 gauge fields, there again should be the Wilson loop operator in here. For whatever trajectory our particle is following. Now in this classical calculation over here, I didn't take the Wilson loop operator into account. But if I was going to honestly do a semi-classical analysis over here, I should include it as a functional of the trajectory in what I would call the classical equations of motion. So in other words, this equation should look more like this. There should be then a force term coming from the interaction of the particle with the Wilson loop, or the back reaction of the Wilson loop on the particle's trajectory. This is an ordinary integral. I put it in brackets because I'm not sure what the measure is. You have to adjust the measure according to the regulator in this kind of integrals. Yes, it should be. And maybe a minus log W. the sign might have to also be adjusted. Actually, I think it is minus log W. Okay, so it gives a forcing term, which in a sense back reacts on the trajectory. But just like in the straight line, actually, this forcing term, or d by dx mu of w, it's basically the same thing. When evaluated on a circle, is equal to 0. And that's simply because the high degree of symmetry of the circle. Right? D by dx mu is going to produce a vector-like quantity, and then it's averaged over something which has rotational invariance, and no vector can survive rotational or a rotationally invariant average, and so you simply get 0 here. That means that the circle that we found is actually a solution of this bigger equation, and so is again a valid semi-classical solution of this problem up here. Then the semi-classical limit, here this should approximately be e to the minus this action we found times w for a circle, for the circle trajectory that we found. And this we could set out to compute perturbatively, and we'll talk about that in a moment. But first, maybe I should say, what do I mean by semi-classical, really? Well, if you went to integrate the fluctuations here around the classical solution, there'd be some from the action, which aren't too bad. The action is quadratic in x's. So at least as far as the x's go, it's quadratic in them. I could think of integrating the fluctuations of x first, and that would be almost an exact integral. I'd have some complicated integral over t to do after that. Okay, but indeed I could think of doing that. But once you include this thing was simple evaluated on the circle. Well, maybe not. That's something on, its derivative was simple, it's 0. But the quadratic fluctuations, if you expand it to delta x squared, where delta x is a deviation from the circle, will be some big complicated thing, basically unknown to us, to all orders. And so the determinant would include that complication. Even the fluctuation determinant would be very difficult to compute beyond perturbation theory here. So it's that part that's being ignored, and what kills that part is the mass being large. Large compared to the electric field here, it makes this exponent big, but large basically compared to the fluctuations of the geometry of the circle inside here. So that's what's making this semi-classical. This is really truly a heavy particle limit here, and heavy compared to the size of the the size of the circle times the mass should be a large number, which this is this exponent here is basically the size times the mass. Okay, so that's what's semi-classical about it. Now we could set out to study this Wilson loop perturbatively, and it has a very nice structure that historically in the subject was maybe the first of the really interesting Wilson loop results. Of course, many have followed since then, and I'll mention almost none of them, but there's a very large number of quasi or even exactly computable Wilson loops in this subject, and Wilson loop correlators of Wilson loops with other things, and this is one of the first ones. So let's see, to calculate the circle, what do we do? Well, for a general trajectory in the leading order in perturbation theory, we had the following expression. This was for an arbitrary trajectory, if you remember, and there was here lambda over 16 pi squared, integral over 2 time parameters. Then a numerator something like this. Right, where this is a dot product on this side. And then x of tau 1 minus x of tau 2 squared downstairs. And then higher orders. Okay, so this was something that one can derive using perturbation theory, which is actually valid for any trajectory. And now we can evaluate it on the circle. When we plug in the circle coordinates into this thing, what we get is this entire combination of propagators collapses to 1/2. Doesn't depend on the radius of the circle, because that scales out. And then you could just see how it goes. Here's the modulus, which is 1, right? The tangent to the circle, well, not 1, but some constant, probably 2 pi. This is also 2 pi. Here's minus the dot product, so this is like the cosine of the angle between the two. And downstairs, you also have x squared, which is 2, minus 2 times the cosine. So a factor of 1 minus the cosine of the angle between the two cancels out. And there's a factor of 1/2 left. So the effective propagator here is a constant. And that, of course, lets one do this integral, because then one just has to integrate over these things. These time derivatives, this is not written very clearly here. These are tangents up here. These time derivatives might produce some 2 pi's or something. I'm just looking here to see if I actually have the weak coupling limit in my notes. This was the integral from 0 to 1. These produce 2 pi, so there's 4 pi squared. I think that's what it is. 1 plus lambda over 8, and then higher corrections. Allows you to do this integral easily, first of all, so that's nice. We can do an integral without really doing anything. That's always a good thing. But we can do a lot more than that, because here we have a constant propagator. This is a propagator that joins a point on the circle to a point on the circle, but anytime such a propagator occurs in higher order diagrams, it's just a constant. In fact, if we look at the diagrams that have only propagators of that kind, they're rather simple to compute. Well, not really simple, but if the propagator is a constant, there's no Feynman integrations to do or anything like that. One just has to solve something like the time ordering problem, right? The order of integrations of the stuff, of the time arguments of these things, and then some group theoretical factors, right? The insertions of these joint representation objects on a Wilson loop and take a trace. So you might expect that for the circle Wilson loop, Feynman diagrams like this are fairly easy to compute. And in fact, they don't even have to be like this. They don't have to be planar. I don't have to restrict myself to one large n here. I could really think of doing any of these things. Okay, so to solve the combinatorics, if one can do it, one can sum up these diagrams. There are, of course, a whole bunch of diagrams left out. Not all Feynman diagrams are like this. Right? There are other lines that have vertices in them that are left out of this, so we'll have to think about what to do with them. But let me first discuss how to sum up these. So the main thing to do is to solve the combinatorics of where these lines are inserted here and the trace is taken. And that can nicely be done using a Hermitian matrix model. In other words, one basically reduces the Wilson loop to something where the propagator is a constant from the beginning, the space-time structure isn't there. And the problem looks something like this, a trace of something without a trace in a matrix model of basically a loop operator like this, where the partition function for this matrix model looks like so. It's an integration over Hermitian matrices. So this has n squared real variables that you're integrating over. And then it's actually just a Gaussian matrix model. Okay, so with this partition function, this expectation value is taken by just inserting this operator, in a sense, into this partition function and doing the integral. And this integral can be done exactly using the method of orthogonal polynomials. I won't do that here. I'll just quote the result. Actually, I'll quote the result for large n, because that's the one that's mainly of interest to us here. In fact, what we've said here in this model is really only good for large n, and that's because I didn't include further loops of this W boson field and so on. So over there, I'm more or less stuck with large n, although for the Wilson loop here, I could certainly go beyond it if I wanted to. So at large n, this is rather easy to solve. There are standard techniques. I won't go into them. But what one basically does is diagonalizes the matrices and looks for an eigenvalue distribution, which is a saddle point of the integral, and then it's a saddle point approximation. And of course, for a Gaussian matrix model, it's this famous semicircle distribution of eigenvalues and so on. When you compute what it is at large n, it's this, of course, times n because of the trace, is just this modified Bessel function, which is a function of the square root of lambda. Okay, so here I've summed up all diagrams of that kind to all orders and gotten some closed form expression, which is a function of the coupling constant. Diagrams that I've left out, the leading order ones look something like this. They're ones with internal vertices in them. Stuff like that. These one can calculate. They're not really easy calculations because they're 3-loop diagrams. But it's not that hard either, in n equals 4. Just plug in the propagators and play around with them. And in fact, the leading order ones cancel out. And that might lead you to conjecture that this cancellation has something to do with supersymmetry. Actually, the calculation had something to do with superconformal symmetry, because in the calculation where they cancel out, you do a dimensional regularization, and the cancellation doesn't actually work until the dimension is put back on 4. Okay, so the singularities all cancel, and then you put the dimension back to 4, and then these things go away. So you might guess that they might work to all orders, and then that this is, in fact, the exact result. But of course, it's just a guess at that point. But next week, you're going to hear about a technique called localization, And this has actually been proven using localization since all of this stuff. And what you do is you put the n equals 4 theory on the 4 sphere, and then for certain classes of observables, with half BPS observables, for example, including the circle Wilson loop, which is a half BPS one, one can modify the theory, the standard localization techniques, to project it onto something which has less degrees of freedom. In fact, one could rewrite the whole theory as this matrix model. Okay, so the localization projects the n equals 4 partition function onto this matrix model. And then in this matrix model, this Wilson loop qualifies as one of the operators that the localization applies to, that you can use it to calculate the expectation value, and the Wilson loop projects onto this thing. So the entire n equals 4 theory for some class of observables collapses to this matrix model, and the Wilson loop is one of those observables. And then in the large n limit, the solution of the matrix model is this. So here's an example of something that you know from the gauge theory side to all orders in the coupling constant. So then the natural question is, I can take and extrapolate this to large coupling and ask if it perhaps could be compared with the string theory side of such a calculation. So at large coupling, this looks something like this. It has e to the root lambda, which is the thing that you might hope to compute easily on the string theory side. And then even the prefactors are known. It's something like 2n over root lambda times lambda to the minus 3/4. So on the string side, actually, one will reproduce this rather easily. This other stuff, to my mind, has never actually been honestly reproduced. It's very difficult. On the string side, this would come from the semi-classical, the corrections to the semi-classical limit of the string sigma model. And that really means you have to drag up everything, the fermions, the ghosts, all the stuff in the sigma model, and integrate the fluctuations. And that turns out to be technically quite difficult. So there's quite a bit of literature about it, but I don't think there's ever really been an honest beginning to end calculation of the prefactor on the string side. So this is an example where actually the non-perturbative gauge theory is a little bit more powerful and easier than the string theory side. But in any case, let's go over to the string theory side and discuss how to perhaps get the same thing. So on the string theory side, all we're calculating is an amplitude for the open string. So this should be the lambda much greater than one side. And our amplitude, well, it should be given by integrating the partition function with appropriate boundary conditions for the open string. Right, the open string sigma model. Of course, that's a tall order because it's not even easy to write down that sigma model. And we'll do it semi-classically. And that has a great advantage that we only really worry about the bosonic part of the sigma model. And that we can write as the Polyakov action, for example. And before we did it using the Nambu action, but just for a change of pace, let me try to do it using the Polyakov action. So this would be an integral over embedding functions, e to the minus action. And the action comes from writing the Polyakov action on the ADS 5 cross S5 background. I'll omit the ADS 5 part because it's trivial. Pardon me, the S5 part. So the Polyakov action here would look something like that. Right, it's the string embedding functions, embedding it in the ADS5 background. Here it's sitting at a point on the S5, so that part you already know the classical solution of. The fluctuations we're not ever going to look at, so we don't worry about it. So this is the Polyakov action, and if you use the Polyakov formalism, then besides the action, there should be some Virasoro constraints. So constraints on these solutions would look something like this. And there should be some boundary conditions. In fact, I haven't quite written all of the Polyakov action there. There's a little more to it because I want to couple the electromagnetic field. So how do you couple that to a string? Of course, you couple it to the boundary of the open string. You couple it to that boundary of the open string that lives in the D brane where the electric field is. And so one should add a boundary term here. A line integral along the boundary of the abelian gauge field. That, of course, will not change the equations of motion, which looks something like this. And should be augmented by the Virasoro constraints, but it does appear in the boundary conditions. And I haven't actually written the boundary condition in my notes, but it is a boundary term that has a derivative in it. And so instead of the Neumann boundary condition that you get for the open string, right, in the Neumann directions, you get a sort of a Neumann-Dirichlet mix of boundary conditions with background gauge field being a parameter in there. Okay, so there's a boundary condition. Containing the background gauge field. And I guess I can leave it as an exercise for you to figure out what it is. But it's not that hard. It's exactly the same boundary term as the term that we added to the particle action, actually. In a sense, you're just treating the charged endpoint of the string as the particle. And then just applying the variational principle and looking at what you need for the boundary terms to to vanish when you do the integrations by parts that you need to do with the variational principle. You can see what the boundary conditions are. And that's what introduces the electric field into the string, into the string theory problem. Okay, one also needs some boundary conditions. So here the open string configuration looks something like this. In my anti-de Sitter space, there's this probe brain sitting here in the middle of the space like this, and I have some trajectory on the probe brain. The boundary condition is going to be such that it forces the boundary of the string to go in a circle here. So the string should come to the probe brain at a circle and then hangs down into the anti-de Sitter space and does whatever it does down there. And actually it will turn out that this disk-like world sheet is the appropriate one. It always has lower energy than a world sheet that hangs down and intersects the horizon. And so what one gets is that at the boundary, let me call the string coordinates tau and sigma naught is the space coordinate. Then I'm coming up to the edge of the string with this. Well, they're both Euclidean, so it's not really space and time, but sigma naught is the one, sigma going to sigma naught is approaching the boundary. That is this boundary. So tau goes around this circle and sigma goes transverse to it. That this x coordinate, well, it should look a lot like what we had in the particle case, some radius times cosine 2 pi tau sine 2 pi tau and 0. And then the radial embedding at the same sigma naught coming up to the boundary, well, it should come up to the radius at which the probe D brane is embedded. Okay, so this is a bunch of, well, slightly nonlinear equations, but they can be solved. And actually, the easiest way to solve them is to kind of guess what the solution might be using symmetry. So there are two ways to do that. One way is to realize that, well, there's a lot of symmetry here, like conformal-like symmetry. For example, there's a conformal transformation, a singular one, but albeit one, which will transform the infinite straight line that we had before into a circle. All right, there is such a transformation. And that transformation is actually a symmetry of the background ADS space. So one could simply take the embedding functions one had before and do the transformation to get the appropriate ones for the circle. When this solution was first derived, to my knowledge, in Maldaceno's paper, that's what he said he did. There's another way to do it, and that's just to guess based on symmetry that this two-dimensional space would be a highly symmetric one. A highly symmetric one embedded in ADS, well, what could it be? ADS2, with some appropriate ADS2 radius. That would also be a correct guess. In fact, the previous one for the straight line was also ADS2, just a slightly different kind of ADS2. Just time was oriented differently on it. And this is also an ADS2. So if one guessed that, that would be a good guess, and that's indeed correct. and then one could unwind it into a solution for these equations. So let me write what the solution would look like. Okay, so that embedding equation looks like, solution looks like that. And then R looks like R0. Looks like that. And then this sigma naught, which appears in the boundary conditions here, is related to the radius by an equation like this. And then the radius, well, it's actually determined by the electric field by imposing that boundary condition. But I won't quite do it that way. I'll keep it arbitrary. I'll plug this into the solution. And then one can also determine R by an extremum condition, just extremizing the solution as a function of this radius R. Yes?
So we're talking about the transformation to map the circle, transformation to map the circle into the line, the straight line.
Yeah, or line into the circle, yes.
So is this transformation? Well, I don't think.
This is the solution you get once you've done that.
Yeah, but I don't see a line there. There is cosine and
No, this is a circle. Right? So at every depth, this is a circle. So sigma increasing goes down or decreasing. Is it decreasing or increasing? It's let's see. This is monotonic. So this is sigma increasing goes down into here and then it pinches off. Right. Right. So this is the equation of this object here. Okay, what I'm saying is you can get this by conformally transforming the previous solution. But this is now the solution. Okay? Just to be clear. So this
walks away from the bracket.
yeah. So this is the solution. This obeys these equations here, and it obeys these constraints here. And it has these boundary conditions, but I haven't yet imposed the boundary condition for f mu nu. That would determine this radius, and I'll do it by a trick later on. The trick is just plug this into the action and then minimize the action as a function of R. It'll have the electric field term in it, and that will feed the electric field into R.
The x-vector at the top right has 4 components, but down here it has 3.
That's because this down here has got a misprint. It's a 4-dimensional Euclidean space.
Sorry, can I just clarify?
Yeah.
So, are you saying the radius of the circle depends on the sigma coordinate? And so this shape pinches off?
Well, this sigma 0.
So I guess I'm confused as to why the shape isn't just a cylinder that extends from R0 to R0. Why does it pinch off and create this kind of like net shape?
This is smaller. So actually, I'm not sure the other one is even a solution. This is the extremal surface that has that boundary. I'm not sure I have a better explanation than that. Right? The thing that hangs straight down that has the same shape and goes all the way to the horizon always has bigger area than this.
In that picture,
Yeah.
the Fermion is not the string that would represent the W loss of that,
Well, in a sense it is. So you think of the endpoint that traces a circle as the end of that string. but somehow down into here it dissolves into the geometry and makes a disk amplitude instead of maybe the cylinder amplitude that you were expecting. And that part is just some of the magic of ADS-CFT. I can't say I have a good understanding of what looks like a mixture between disks and cylinders, except I do, from the other argument, expect this to go like n, because the Wilson loop went like n, which is 1 over G string, which is appropriate to the disk amplitude, actually.
So you solve the boundary to be on the right in the middle.
That's right.
Use compound transformation to find the Seeger geometry, the surface.
That's right. Well, one can do it. It's not really the way I did it. But if you have a straight line here, you can find a conformal transformation that maps it to this circle. And that conformal transformation is in the symmetry group of the ADS background. So it could map the whole thing into this. Yeah. And that does work. That is the way Maldacena said he did it in his original paper, where he did this computation. Actually, what I did is I just wrote down an ansatz for ADS2 with the right boundary condition, and then extracted the embedding functions from that by solving the ansatz. Actually, the ADS2 is rather simple. It looks something like this: x squared plus 1 over r squared is equal to r squared. That's Euclidean ADS2. Where this x squared is really the, well, it's not really this, it's, well, actually it is. Well, it's some version of this. It's actually time squared. It's some quadratic form like this that defines ADS2 that you can just write down, fit to that thing, and then coordinatize, and you have it. Okay, so that's a bit of a long story, but you can take this and stick it into the action. And get what S is. So if you plug that into the action, it comes out looking like this. The first two terms are from the Polyakov action, basically from the two non-trivial terms in the Polyakov action, and the last term comes from the boundary term. And you can see it's just the area of the disk on the boundary times the electric field, just like it was for the particle. Then to determine the radius, I can just do it here by extremizing this as a function of radius. And that will have solved the boundary condition and coupled properly to the electric field. And what I get in the end is an action that looks like this. I actually have it written here where I've already taken this root lambda times R0 and identified that with the doubly boson mass. If I do that, this action turns out to look like this. Something we saw from the particle as a first term. Remember, this was the same as what we saw with the particle. Then, actually, the Wilson loop term, the correct one, and then some other term, which if lambda was really large would dominate. It looks something like that. But we have to remember we should be working in the large mass limit here. So I would like to throw away this term. If I do that, then we see our amplitude has just the semi-classical propagator part, and then the expectation value of the Wilson loop, exactly like we anticipated from the other side. On the other side, we had the good fortune to be able to calculate something, what we guessed was a good calculation of all orders in lambda, and obtain this result. And here we just get it this way from carefully treating the sigma model in an environment which forces the particle to go in a circle. Pardon?
All of the expressions on here were from the ADS side.
These are all from the ADS side. It came from the boundary term. So when I wrote the Polyakov action equations of motion, E doesn't actually appear in the equations of motion. It's sitting in a boundary term, and then it appears in the boundary condition. I didn't really use the boundary condition. I just left a parameter in the solution, plugged in the action, and then minimized the action together with E to get that parameter. That's completely equivalent to somehow imposing the boundary condition with E earlier on and eliminating the parameter earlier on. It just was easier to do it this way. So this R is that parameter. This is the boundary term in the action. Right? It is just pi r squared, the area of the disk that fills in the circle, the one that's constrained to be in the four-dimensional space. And then this is what one gets by plugging the solution of the equations of motion with the circle boundary condition in. And then one minimizes with respect to R and plugs in the minimum, and you get this expression.
When with the straight case, my understanding is that we solved the number Gross action for the strings.
Yeah.
We pulled this back onto the D-brain action, and then we put the D-brain action into this expression for A. Is that correct?
We use the Nambu action. Yeah.
But then we pulled that back and we calculated the metric on the D-brain, and that gave us the area, right?
No. We embedded the world sheet in ADS. And so the embedding in ADS basically gave us the world sheet metric. And there we really just guessed the embedding. We guessed that an extremal embedding is the most symmetric possible world sheet, the one that hangs straight to the horizon. And if you don't trust the guess, if you have even a little bit of doubt about it, you can just go to the equations and see that it solves the equations of motion that you get from the Nambu action. But we guessed it, we plugged it into the Nambu action, and then we had an equation for the on-shell classical action from that. Here, instead of Nambu, we use Polyakov, but that's really the only difference. We use Polyakov, and we have a slightly more complicated dynamical problem, which we managed to solve anyway. Okay, so this is a story about the Wilson loop, and there might even be a little bit of physics in here. If you resurrect this term and take it seriously, you'll notice that this is a square. It's given by the square root of this minus the square root of this squared. Right? When you take a product of this times this, there's a lambda. That's how you know that. Lambda over 2 or something like that. Right? It makes it a square. So this actually, as a function of electric field, has a 0. So if you decided to trust this for electric fields that are big enough so the action's actually 0, that you must understand is dangerous, right? To really be semi-classical, the action should be big. It shouldn't be 0. But okay, we worked hard to get this far. Let's try to understand maybe the full implications of what we have. So if you trusted this where the electric field is 0, you might think of that as some sort of a phase transition, right? In a sense, the barrier to whatever process you're talking about vanishes there. It's no longer exponentially suppressed because the on-shell action is actually 0. Right? So the exponent here goes to 0. What is that electric field? Okay, so just as a last comment, what is that electric field? Well, you can see what it is by making this thing 0. I think it's E is equal to pi m squared, maybe 2 pi m squared over root lambda. Is that how where it's 0? Or some critical electric field? You might guess that that's a critical electric field somehow. Okay, so in what way is it critical? Well, way back at the beginning of our discussion this morning, which I guess everyone has forgotten about, me almost too, I had an argument for how a D brane floats in ADS, how a D3 brane can be placed at any radius as long as it's parallel to the boundary and the horizon in ADS. And in that argument, I had a Born-Infeld action and an omega 4, which were sort of balancing off. And inside the Born-Infeld action, one could put a gauge field. In fact, inside there should go the world volume gauge field. Turning on a gauge field ruins that balance. And of course, a constant gauge field is a sort of transient state, right? It should have Schwinger pair production, and somehow in the long time limit, it should no longer be like it is. The gauge field should be screened away, or something else should happen. But that's not the real problem. The real problem is in the determinant in the Born-Infeld action, there is something like a determinant of G plus 2 pi alpha prime F and square root. And this is like an electric field. So what happens is this turns into something like the square root of lambda, well, some parameters which have lambda in it, because in the embedding metric there's lambda. We're also at a given radius, r0, so it has the mass in it. And it turns into something which actually goes to 0 when the electric field comes to this value. It's when the electric field achieves the same value as the string tension. That's sort of a known critical electric field for strings. It's just the electric field where the force on the opposite ends of the open string, which have different charges, is enough to start tearing the strings apart. it's the same size as the string tension. Make it a little bit bigger, and it stretches the strings constantly to infinite length, and that should be some sort of a phase transition. Okay, so the critical electric field one could understand by going back to that formula. I won't fill in the details, but it's rather easy to put in the embedding metric of the D3 brane at a given radius. And inside F put the electric field. And you see that this determinant has some parameters minus electric field squared under a square root. And the critical electric field is exactly this, and coincidentally is exactly where this action goes to 0.
Is there a plus
Yes, there should be. Otherwise, what I said isn't right. Okay, it's a good time to take a break, because I've sort of come to the end of what I have to say about Wilson loops, and I welcome questions either right now or during the break. Okay, well, that was a fairly light-headed introduction to Wilson loops. I didn't do anything that was really difficult. All equations were solvable and were solved, and it's a much bigger subject than what I talked about, but I think I'd like to go on to something else, and something maybe a little bit lighter for this late hour. And that's a discussion of holography using probe branes. So in this discussion, we did use a probe brane. We use it as the place where the end of the W boson, the string that represents the W boson, lives. So we've already gotten used to using probe branes, but there are, of course, many other possibilities, and I'd like to talk about, well, one of them in particular. And that is, instead of putting a probe brane so it slices ADS this way, like our D4 brane, to put it with a different orientation so that it goes something like this. Slices the ADS space in half that way. And what I'll use it for is to make a certain kind of defect conformal field theory. Okay, so far away from that brane, the physics should look still like n equals 4 super Yang-Mills, or more or less like the other, like the string theory dual of it. And close up to the brane, there should be some other degrees of freedom that are basically associated with the brane and in a sense live on them. Now, there isn't an obvious reasoning that ADS CFT should work with this configuration. One almost should go back and do the arguments over again. I will assume that the brane is a probe brane and that there aren't if there's more than one stacked together, at least there aren't very many, that their number is much less than the number of D3 branes that we use to get the geometry. And the fact that the number is small enough that it doesn't back react on the geometry. So if we have some number of probe branes, let me call it NF, NF here should be much less than the parameter we were calling N. Yes?
Where is the N brainstem?
It just goes to the horizon. So for now it goes to the horizon. There are arguments. This science sort of began with some papers by Randall and Karch. Which inserted a probe brain into the black brain solution and tried to argue that the same arguments that give you Maldaceni's correspondence give you something here, where in addition to the degrees of freedom that live near the horizon that we talked about before, there are some new ones, and these are basically strings that connect the probe brain to the horizon and then end up living as degrees of freedom on the probe brain in the field theory dual. That argument is a little bit looser, and of course was loose enough already to my mind. So this is on a little bit softer ground than pure ADS CFT. But there have been some pretty non-trivial checks of it. Some things, again, using localization lately. This is for the probe brain that we will use a superconformal, is dual to a superconformal field theory of some sort. It's fairly well protected by supersymmetry, but has enough supersymmetry that one can formulate localization arguments and use them to calculate various things. Actually, it's very few things so far. But there are some checks of the duality for this configuration too. Much less than for good old garden variety ADS CFT, but they are there. And there are some other things that one can test, which I will talk about after a while. I guess by Friday, there's still a long time left. We will get to them. There are some things that one can compute in this scenario and extrapolate across between weak and strong coupling, and which do happen to agree rather well. So this is something that perhaps could work. Randall and Karch is from the early 2000s. It was sort of a pioneering paper. There's a much better one. I apologize for not remembering the numbers of these. I am going to post some notes on my web page. In fact, maybe in a while I'll give you the coordinates of the web page. You can look at them there, where I will put these a little better. There's another classic paper by De Wolf, Friedman, and Oguri, which works out a bunch of the properties of such a system. Does some calculations in the weakly coupled defect conformal field theory, does some calculations on the strong coupling side, figures out what field theory lives on the defect on the quantum field theory side. They can do that because it's completely determined by the symmetries. So if you impose the residual supersymmetries and R symmetry and so on, then write down all of the marginal operators. Well, they don't exactly do it that way because they work in superspace. But the field theory that lives on the defect on the field theory side is completely known. It's complicated, but it's completely known. The field content is known. The Lagrangian is known. And so this is an interesting place to look. On the defect, yes. Yeah. So everything is known about the defect field theory as far as Lagrangian goes. It's quite a bit more complicated than just n equals 4, but it is known sort of concretely what the dual field theory is. And that's in the case where this probe brane is a D5 brane. And it's a D5 brane with this sort of orientation. So first of all, remember we had D3 branes, which sat at points in the first 4 space-time directions, pardon me, which filled the first 4 space-time directions and sat at points in the others. And now we put a D5 brane there. And we want it to be a defect theory, so it shouldn't fill all the space-time directions. It should leave one, so it can be a planar defect, 2 plus 1 dimensional defect, bisecting 3 plus 1 dimensional space-time. Right, so here's the 2 plus 1 dimensions. Leave this one open. And then it should have a 6-dimensional world volume, so fill 3 more of these. Okay, so it should be something like that. Now this is a so-called ND equals 4 system. How do I get ND equals 4? I look at this table and the XO, OO doesn't count, XX doesn't count, XO counts for ND, Neumann-Dirichlet boundary condition for the open string, and there's 1, 2, 3, 4 of them. So if you look in Polchinski's book, I think it's somewhere deep in volume 2, I don't remember exactly, he classifies these things. And an ND equals 4 system is one that happens to preserve half of the supersymmetries of the D3 brane system. So this brane combination will be half supersymmetric. And in fact, when embedded in the de Sitter space like that, it will preserve all of the anti-de Sitter symmetries that the brane world volume preserves. So the bosonic symmetries you can almost read off from here. There's 2 plus 1 dimensional Poincaré. Then over here, there's an SO3 or SU2 rotating between these 3 extra dimensions. And over here, there's another SO3 of going away from the brane in directions that it doesn't wrap. Okay, so SO6 of the D3 branes appears to be reduced to SO3 cross SO3. The 3 plus 1 dimensional Poincaré symmetry reduced to 2 plus 1 dimensional. But of course, then this is later on enhanced to a conformal symmetry, and in fact to a supersymmetry, a conformal supersymmetry. The conformal, superconformal algebra is the one called OSP44. Okay, so instead of 16 supersymmetries, it has 8, but then those are doubled in the usual way when embedded in a conformally symmetric object and taken back to 16. The most symmetric configuration of that D-brane sits in ADS5 cross S5, and it sits on a subspace which is ADS4 in the ADS5, gotten by just killing off one dimension, so splitting the ADS4 in half, and then on the 5 sphere it sits in an S2 subset of S5. That S2 wraps these 3 directions. Right? In fact, the radius of the 3 directions turns into the ADS radius, and the rest wraps the 2 spheres that these turn into. And then it sits at the origin in these 3 directions. Right? If it went away from the origin, it would break this symmetry, the classical configuration of the brane. So it sits right at the origin, which means that this is a maximal S2 on the S5. In other words, if you write the S5 like this, x1 squared plus so on plus x6 squared equals 1, a unit S5 sphere, for it to be maximal here, it should sit at the origin. It means this S2 satisfies x1 squared plus x2 squared plus x3 squared equals 1, and the other x's are 0. So that's, in a sense, where the brane sits in these transverse directions. And that's a point with a high degree of symmetry, of course, and that's, in a sense, why this is such a nice symmetric solution. Okay. The field theory on the brane is, if there's just one brane, is a single conformal, a single hypermultiplet, which contains a scalar field and a spinor field. So on the field theory side, the defect field theory looks something like this. I won't write the whole thing because it takes about 3 lines when written in component form, but I'll write just the kinetic terms, the terms that you get when you go to weak coupling. When you turn off the coupling constant turns out to be the same lambda as the coupling constant of the surrounding n equals 4 theory. So on the brane, this looks something like this. It's a 3-dimensional space-time. Then there's some complex scalar fields and some complex spinor fields, which are superpartners of the scalar fields. The scalar fields are actually a spinor representation of this first SO3. So the scalar fields are spinor of SO3, the first one. Now let me distinguish them somehow. Write a tilde over the second one. These guys are a spinor of SO3 tilde, as well as being a spinor of the SO21 Lorentz symmetry in the 2+1 dimensional space. Okay, so this is relatively simple until you write the interactions. The covariant derivatives here couple to a few things. One is outside of the defect, in the bulk, the 3+1 dimensional space outside, is n equals 4 super Yang-Mills theory. So in that n equals 4 super Yang-Mills theory, of course, there's the gauge connection of n equals 4. That appears in this covariant derivative here. These, in the n equals 4 gauge symmetry, the SUN that that the connection transforms under, this is actually a fundamental representation field. So these are fundamental representation fields of the bulk gauge group. They are also U1 charged. They have a global U1 charge. That U1 charge is actually just the gauge symmetry of the D-brane. On the string side, the D-brane actually has a world volume gauge field, but gauge symmetry in the bulk of the D-brane turns into global symmetry on the boundary. And so there's a global symmetry on the boundary corresponding to the U1 gauge field on the D-brane, and that is the thing that just transforms the phase of these component fields. Okay, so the other thing is that this is completely fixed by symmetry. And again, the coupling constants then are G Yang-Mills and N, just like in N equals 4. And you might put another one here. If you had more than one of these branes, you could consider stacking these D5 branes up. That would put a number of D5 branes. It should be much less than N, but there could be another parameter we would call the number of flavors. How it appears here is it would just give a number of copies of each of these. And instead of U1, there'd be a UNF flavor symmetry. And of course, if there are multiple branes here, there are gauge fields living on the string side on the bulk of the D brane, right, which would be SUNF gauge fields, and that would then correspond to this global symmetry in the field theory.
If I have 4 branes, I have more copies of Q only or also on side?
Sorry, both. Well, these are super partners. They have to have the same number, actually. So you add both. So these would get a flavor index, and they're just degenerate. And they're complex, so they would just simply transform under UN as fundamental representation fields. So they're called bifundamentals because they transform in the fundamental of the bulk gauge group, and then they would transform also in the fundamental representation of this extra UN flavor. There should be an NS5 version, but I honestly don't know. All right, there should be a S-dual NS5 version of some kind. The D3s are self-dual, so, but I don't know much about it. I can't really tell you much. Okay, so this is a way to make a defect field theory, assuming it's correct. So I think in my fairly limited time here, let me just try and explain why this would be of interest. What kind of physics do I want to study with this kind of model? So let me just assume the duality is absolutely right. Let me not question it. So what can I learn about strong coupling physics by studying this model? Right, so I want to learn something about quantum field theories like that by looking at the behavior of the D5 brane. And I might actually compare these behaviors just to see if it's reasonable. In fact, that's something I like to do. study the behavior on one side, on the other side, kind of see if they fit together in a reasonable way. Actually, the physics of this system has been studied quite a bit. There are a series of papers whose authors I've forgotten. Well, one of the authors is Nick Evans. And then he's had various collaborators, and he's written a few papers about these, where they basically figure out a phase diagram for this system. What do I mean by phase diagram? Well, what they do is they figure out how to put a U1 charge density into the system. So for one brane, U1 is just the phase symmetry here. So a charge density is really just a U1 charge density for these fields. They figure out how to turn on a charge density, and they figure out how to subject it to an external magnetic field, also in that U1. So that's like studying some condensed matter system. Well, no condensed matter system really looks like that, but you might stretch your imagination a little bit. Some condensed matter system with a defect that has, I don't know, relativistic particles. So there are defects with relativistic stuff like graphene and some other semi-metals. None of them will be supersymmetric. Okay, so you're not quite there, but anyway, you might imagine that. Introduce an electric field on this defect system, a charge density, and just study as a function of those things, and a temperature, by the way, also a temperature, what the phases of the system are. And there are some rather dramatic and rather interesting phase transitions here, which they noticed. I didn't notice, they noticed. And I'd like to talk about one of them in particular, and that's what happens when you put a magnetic field. So they didn't talk about this side at all, but on this side they figured out how to put a magnetic field on the D brane. So this magnetic field doesn't couple to the stuff in the bulk. I should really draw a field theory picture of this one, because much of the time I'm talking about it. So let me draw a field theory picture so as to be a little bit clearer. Okay, so that thing is presumably dual to four-dimensional spacetime, populated by n equals 4 super Yang-Mills theory, with a defect in the center, cutting the spacetime in half. On that defect lives this field theory. Out here in the bulk is n equals 4. Okay. So the magnetic field that they put is here, some B field perpendicular to the brane. They also learned how to put a temperature and a density, but let's, for now, not worry about them. Just introduce the magnetic field. Then they go over here. They figure out how to model this over here, which is basically by putting a constant world volume magnetic field on the brane here. So it's not that difficult to do. We can figure out how to do that ourselves. Dredge up the Born-Infeld action, put a magnetic field in there, get some equations for the brane embedding. Without the field, this is a solution, this maximally symmetric thing. You might guess it's a solution. It would just have to be. With the magnetic field, that ruins a bunch of the symmetry. What's the solution? What they find is immediately when you turn on a magnetic field, any field at all, you have to realize this is a scale invariant theory. Okay. Magnetic field has a dimension, so as soon as you turn it on, there's no difference really between infinitesimal magnetic field and infinite magnetic field, because it's the only dimensionful parameter. As soon as you turn maybe that's better. Except it won't stay there. Okay, let's try that. As soon as you turn it on, this D-brane changes character completely. What happens is it truncates somewhere up here before it gets to the horizon. It simply pinches off and leaves a gap here. That is quite a dramatic change in the nature of the physical system. What happens intuitively is these strings, whose zero modes make this theory, these strings then have a minimum length. They have to stretch from the horizon up to the bottom of the D-brane. That on this side means that these fields get a mass gap. They get a mass gap by breaking one of these SO3s. It's actually this one. And that's in a sense because the S3 that's wrapped moves away from the most symmetric point on the 5 sphere. It has to move away in some direction. That breaks the second SO3, and that gaps a fermion spectrum. So that's basically chiral symmetry breaking. A beautiful example of it, well, driven by strong interactions. It says if you put a magnetic field in here, and if the interaction is strong, chiral symmetry will break. There will be a mass gap induced for the fermion fields, and they'll behave as if they're massive. A huge change in the electronic properties of the system, because before that, electronically, it's gapless, actually. You probably don't have a way of knowing that, but conformal symmetry here can be used to calculate the AC conductivity of that thing, for example, and the AC conductivity is just a constant. Once it gets a gap, the AC conductivity, well, below some frequency is 0. It's an insulator. Okay, so that's a huge difference. What's interesting is to ask if you can see it on this side. So at a late time of day, we could think about that question a little bit. So what if I came over here and introduced a magnetic field? What happens? Right, so put it on a magnetic field in these covariant derivatives. What is this theory like? In other words, turn off the coupling constant. Go from infinite coupling to zero coupling and ask what do you expect to happen there? Well, you have some bosons in a magnetic field and some fermions in a magnetic field. We could turn on a magnetic field on the brane. We should really be solving the Born-Infeld action, which has the brane gauge fields in it, so varying it by them should give some equations. But just like in Maxwell theory, a constant field solves those equations. Right? In Maxwell theory, a constant field is always a solution. Right? In Born-Infeld theory too. Constant field will be a solution because when you vary a mu, you get derivatives. Well, maybe covariant constant if it's a curved space, but so there is a kind of a modulus here which allows you to turn on magnetic field. And what it does is really turns on a magnetic field that's perpendicular to the brane, or to the defect in the actual field theory. Okay, well you have some bosons and fermions. You turn on a constant magnetic field, we know what the states of these things look like, right? They just get this Landau dispersion relations, Landau levels. The bosons, their dispersion relation looks something like this. Inside here is the magnetic field strength, and then there's some sort of 2n plus 1 harmonic oscillator quantum numbers. Right? If you write a relativistic wave equation in a magnetic field, constant magnetic field, it looks like a harmonic oscillator equation. For the Hamiltonian, the frequency on the harmonic oscillator is like the magnetic field. There's a 0-point energy of the oscillator that gives the plus 1, and then this is the oscillator number, and n is equal to 0, 1, 2, 3, and so on. So this is a spectrum of the bosons. The fermions are a little bit different because they have a Pauli Hamiltonian. If you square the Dirac operator, that means there's plus a term with a magnetic field. So fermions, their frequencies actually look like this. So the magnetic field has ruined supersymmetry. The spectrum of the bosons and the fermions are different. The 2n here also starts at 0. So there's a 0 mode of the fermions in a magnetic field. That is a Landau level that sits right at 0 energy. And then, of course, being fermions, they have positive and negative energy states. Then there's some negative energies and so on. Okay, so these two are different, and that's interesting. What else is interesting? Well, we could study what the ground state, what the very low energy states would look like. So let me find a nice place to draw, well, okay, let me draw them in here. The very low energy states. So the fermions, and say this is n equals 0. And actually there are two kinds of fermions because they're a doublet under this SO3. So in a sense, even for one D brane, there's two towers of the fermions. And then somewhere in the middle is the n equals 0 state. And then the bosonic levels are in between these. If you're worried about very low energy states, what you're supposed to do is fill up the fermion negative energy states. So all of these are full. And then to have charge neutrality, half of these should be full. So these are half filled. And then if you have very low energies, too low of an energy to excite a boson, this is basically what's going to govern the physics of the ground state. Notice that half filling these states is hugely degenerate because the number of states here scales like the magnetic field times the volume, like the total magnetic flux through this surface, which is infinite. So these are infinitely degenerate, and you should choose half of them to fill. Any half that you choose will have the same energy as any other ones. So this is degenerate. Exciting a boson, it comes up the energy somewhere here. So there's this little window of energy where we don't actually have to worry about the bosons. And the original supersymmetry of the theory isn't very important. It is just a problem of deciding how to fill fermion zero modes. And it looks pretty degenerate. In fact, it looks hugely degenerate. Without some interactions, it's difficult to resolve this degeneracy. Every state has the same energy, and that's all there is to it. If I turn on some interactions, one has to decide what the important ones are. At large n, the ones that are going to be important are actually the ones that are mediated by the bulk gauge fields. At large n, the interaction that's emphasized is what's called the exchange interaction from the bulk gauge fields. So let's assume coupling is weak, so that's a weak interaction, but it's still there. That interaction, even though they're non-abelian gauge fields, is a lot like a Coulomb interaction. In fact, it has the same range, the same 1 over r potential, just because of conformal invariance, and the same sign. It's repulsive. So if you turn on a little bit of interaction, these fermions are repelling each other. That might help to resolve this degeneracy. In fact, in this case where it's exactly half filled, it does help. That's because they're fermions. first of all. So they have a Pauli principle. Secondly, they're repelling each other. So to minimize the energy, they like to get as far away from each other as possible. They have to have an antisymmetric wave function. So they want to have a wave function which in the space coordinates is as antisymmetric as possible in order to keep them as far apart as possible. If it's as antisymmetric as possible in the space coordinates, in this isospin index, it should be as symmetric as possible. Right? So if it's symmetric in isospin, it can be totally antisymmetric in the space coordinates. Symmetric as possible means, well, I have just enough fermions here to give them all the same isospin index. Right? There's something completely symmetric in isospin, and therefore completely antisymmetric in space. And they stay as far away as possible from each other. And that distinguishes this, even with a tiny, tiny weak interaction, as a lower energy state. In other words, makes a gap in the spectrum between this guy and this guy. That gap in the spectrum, well, that's our magnetically induced chiral symmetry breaking. It's like a condensate of psi bar psi. So it's exactly what's seen on the strong coupling side, extrapolated down the weak coupling. It's in fact in condensed matter physics a known phenomenon that's seen in the Hall effect, say the integer Hall effect when the electrons have spin. It's just the same thing. You have a completely filled Landau level, but the electrons have spin, so there's twice as many places. It means you have a half-filled Landau level, actually, and it's completely degenerate. And then what happens is all the electrons want to have the same spin. Just like here, they want to have the same isospin. That phenomenon is called quantum Hall ferromagnetism because it looks like a ferromagnet. All the spins of the electrons are lined up. So that was seen actually experimentally circa 1990. There used to be quite a bit of literature about it. It was forgotten for many years until it was seen again in graphene, which is this kind of a semi-metal. Well, it looks a lot like this where the bosons are absent. But here at this very low energy, the bosons are not relevant anyway until the splitting gets big enough that it competes with exciting the first bosonic levels. And we don't really know how big that is. One expects the splitting to be of order B, square root of B in energy, the magnetic field, and also the height of this bosonic level is also of order B. So everything's of order B here. And in fact, over here, the gap on strong interaction, the gap is of order B. So we don't know if it ever competes with the bosons. Maybe by this argument, it never does. Even if you actually go to strong coupling, perhaps the bosons never come and ruin the incompressibility of the fermionic state. Okay, so that's called quantum Hall ferromagnetism. And this has actually been seen in graphene in a rather spectacular fashion. So just let me end with this. I see my time is almost over. Let me talk about a little bit about this experimental result. So graphene was discovered 2004. And the first thing that they did were basically quantum Hall measurements. And they had this rather dramatic, sort of famous measurements of the Hall conductivity of graphene versus filling fraction. And there they see a Hall step right at 0 filling fraction. And then the height of the steps exhibits the degeneracy of the relativistic electrons in graphene. So the height of these steps, actually, do I have this wrong, I think, just a minute. Don't write it down. Yeah, sorry, charge neutrality is halfway through a Hall step. Okay, that's fine. That's fine. So charge neutrality is right in the middle of a step, which to a condensed matter physicist was very unusual because it means that the neutral charge state is a half-filled Landau level. That looked really weird to them. Usually something neutral has completely filled Landau levels down in the Fermi sea. Right? A normal semiconductor is like that. So this was already strange to them. The height of these was 4 units of Hall conductance, so 4 times h bar c, which reflected the fact that graphene has 4 relativistic electrons. It was just seen beautifully, the flavor symmetry right there. So this, in the condensed matter world, was rather phenomenal, called the anomalous Hall conductivity. The fact that it seems to be offset like this, the charge neutrality, 0 filling fraction, you're in the middle of a Hall step, and then you see a factor of 4. So this was a great result. I think the experimental papers were found by 2 groups, one in Columbia, one in Manchester. They appeared in back-to-back articles in Nature, and within a few years had thousands of citations. It was really started a big industry of people working on this stuff. When this was studied at slightly higher magnetic fields, slightly better samples, actually not a lot higher and not a lot better, what they found is something quite dramatic. They found that this step actually broke up into steps. So something like this. The higher ones did too, actually. There were more steps up here. But they actually saw this happen. And this is exactly the phenomenon we're talking about here. The formation of a gap right at 0 filling fraction. So below 0 filling fraction, you're filling the lowest half of the Landau level, and above you're filling the other half. And in fact, it's a 4-fold degenerate Landau level, so there should be more steps here, which were soon seen after that. In fact, the SU4 flavor symmetry there was completely broken, basically to U4, completely resolved. And that's called quantum Hall ferromagnetism. And the interesting thing there is that the size of this splitting is like the Coulomb interaction in graphene, which is strong. It's definitely non-perturbative. It's in a non-perturbative regime. So this argument, which putatively explains it, actually is not really valid. It should be strong coupling physics that explains what's happening there. And so the D-brane side of this is actually a better approximation to what's happening than this weak interaction argument on this side. And so that's one place where sort of qualitatively the strong coupling physics from the D-brane actually seems to fit what's observed and tells you something. It tells you that this phenomenon, this ferromagnetism, which you can explain fairly easily at weak coupling, survives into the strong coupling regime. Okay, I've used up my time. Thank you.